Welcome back to Structures Volume 2. So the question now is, if I have one of these structures made of bars and nodes, when can the internal forces really balance the external forces? Remember that we had some force acting, and it could send this space station, if you like, spinning off into space. So, well, we remember that the internal forces are supposed to balance the external forces when I have this matrix equation holding. If y is the internal force vector and f is the external force vector, then f should be A transpose y, where A is the matrix that we constructed painstakingly last time. Well, when could that happen? Well, I guess that happens exactly when f lives in the range of A transpose, or the column space of A transpose. And what's the column space of A transpose? Well, that's nothing except the row space of A. And if we wanted to think about the perpendicular, the orthogonal complements, that row space of A is the orthogonal complement of the null space of A. So what does that mean? That means that these forces can balance exactly when the external force is perpendicular to everything in the null space of A. So, of course, if the null space of A was 0, then you could always balance the forces. But if it wasn't, then you might have a failure of equilibrium. So let's look back at our triangle, equilateral triangle that we had last time. We remember we had three vectors in the kernel, the null space of A. Let's just write down two of them. That is 1, 0, 1, 0, 1, 0, and 0, 1, 0, 1, 0, 1. The third one was the approximation to the rotation. The same difficulties going on. We're going to need to deal with the linear approximation of torque. But instead of doing rotations, let's just imagine what it would take for a force F1, G1, F2, G2, F3, G3 to balance with, say, Z1. Well, that just means that to be balanced on this structure. That means that it has to have a dot product of 0 with Z1, which exactly means that F1 plus F2 plus F3 has to be 0. That is, there's no net horizontal force. Similarly, if I take the dot product of F with Z2, I'm supposed to get 0 in order for force balance to be possible, which means exactly that there's no net vertical force. And if you take the dot product of this force vector with our third null space vector, you'll find that what you are saying is that you need there to be no net torque on the structure. But let's not worry too hard about that. So now let's talk about something called a mechanism. Suppose that I have this structure, and I've fixed the two bottom nodes at 0, 0 and 1, 0. So it's a square. These are the vertices of a square, and I've got my bars in between as the edges of the square. So I pick some normal vectors, n1, n2, and n3, unit vectors pointing between the nodes. So actually I'm going to take n1 to be 0, minus 1, so that'll point the other way. N2 is 1, 0, and n3 is 0, 1. So those are my unit vectors. And from those I can construct A. So A is going to point from... A is going to be the matrix. The first... okay. We construct this in the exact same way, right? I put n1 and I put minus n1 in the first row, corresponding to the first node and the second node. And then in the second row, I put n2 and minus n2, and it goes between the second and third column pairs because the second bar corresponded to between the second and third nodes, and similarly for n3. Okay, but the thing is that I fixed the first and fourth nodes. So the whole first and fourth pairs of columns, I don't need them. I kill them. Make them go away, scratch them out in green. That leads me to this reduced matrix, 0, 1, 0, 0, 1, 0, minus 1, 0, 0, 0, 0, 1. I don't know why I wrote a 1 there. It's 0, 0, 0, 1. So here is my reduced matrix that comes from having fixed the nodes 0, 0, and 1, 0. Nodes 1 and 4. So this A hat is unfortunately still possessing a null space. So the null space of this A hat is spanned by the vector 1, 0, 1, 0. So what's going on is that this null space member, even though I've fixed 2 nodes, so there's no more translations or rotations, there's a structural instability inherent in the structure, and this is going to be called a mechanism for the purposes of this course. So 1, 0, 1, 0. Well, what happens if I apply a force, a unit force, to the right to the 2 free nodes? Well, nothing very good. Remember that even though I fixed nodes 1 and 4, they're still allowed to freely rotate. So when I apply my horizontal force to my 2 movable nodes, what happens is that I start out with my structure in a nice, beautiful square, like this. And then, well, I push the top over. It goes shoop. And now it looks like this. Those 2 nodes are still fixed down there, but the whole thing mooges over like so. So this mechanism, this structural instability, is a problem. Well, so here I have my unstable structure. It has the incidence matrix has a member of has a non-zero null space. So what I'm going to do is I'm going to add an additional bar, a reinforcing bar. That corresponds to adding an additional row in my matrix. That row corresponds with this row here in the reduced matrix because the bar has length root 2. So this thing, once I've added 1 row to my matrix A, and I still look at the reduced matrix, I end up with a 0 null space. I've added a row, which has improved the stability of the structure. Because A hat has no null space, it has no mechanisms. There's this structure will now admit unlimited forcing. It's stable in a mathematical sense. Obviously, if you apply a ridiculous amount of force, you're going to sort of leave the linear continuum where we've been doing everything. You're going to bend your bars and so on. But our system won't be able to detect any of that. Now, in this case, A is square, A hat rather is square. And that means that our system is going to be statically determinate again, just like the springs where the bottom plate was removed. We'll be in a situation where our A hat or our A hat transpose is a square matrix, non-singular, and so it can be, in essence, the internal forces can be determined by the external forces. So if I take, for example, a uniform downward force on nodes 1 and 2 I don't know, I wrote 1 and 2, on the middle 2 nodes here, 0, 1, and 1, 1, for example, gravity, 0, minus 1, 0, minus 1, that's my force. Then A hat transpose times y is supposed to be equal to force. So the internal forces to balance that downward force look like minus 1, 0, minus 1, 0, which tells you that the 2 vertical bars are being compressed equally. And on the middle 2 bars, you see no change. So let's talk about a 3-dimensional case. So you're going to imagine a structure built now in 3 dimensions. What I've drawn here is sort of a tent or teepee kind of thing, a Boy Scout tent, if you like. So I want to be able to analyze that kind of structure in the same way. And it turns out that I really have the same kind of math. So I'm going to need an incidence matrix A, and the way that will relate the displacements to the elongations of the bars. And because that matrix A is really the crucial point in all of this. So what's going on is that I really have the same story. The displacements are going to be 3 vectors now instead of 2 vectors. And if I've got m bars and I've got n nodes, then my new matrix should have m rows. There's a row in my incidence matrix A for every bar. And there should be n nodes, so there will be n displacements of nodes, and there's m bars, and so I ought to have m elongations, and the elongations and the displacements should be related by some matrix, which is A, just like we had before. But now the only difference is that instead of having blocks of m by 3, instead of having blocks of m by 2, I now have blocks of m by 3. So the point is that the first node has 3 coordinates, and so all of the unit vectors that point along the bars have 3 coordinates to them now, and so I need blocks of 3 instead. And u1, u2 through un are 3 vectors themselves because they're the coordinates of change in the nodes. So, but that's really the only difference. So my new matrix A will be m by 3n instead of m by 2n, and I just need an extra spare column for every new coordinate. Now, in 3 space, there are 3 axes of rotation and there are 3 axes of translation. So you actually expect a 6-dimensional kernel for your matrix A, even before you fix any nodes to deal with rotations and translations. So your null space of A should be at least 6-dimensional, but it could be more. You might have mechanisms. So after you fix the nodes, you still need to look for members of the kernel, which are going to correspond to those in structural inherent instabilities in your truss. So now look at our swing set. I've now fixed coordinates for all of the nodes on it. So there are zeros there. You can read them off there. Pause the video if you need to. So here I have this very wonderful, nice picture, and I've in teal here I've drawn in some unit vectors that point along the bars. And so the question is, how can I get the matrix A that we'll need out of this? The matrix A determines everything. So N1 is going to point along this bottom left bar here, N2 will be on the next one, N3 on the top bar between the 2 movable nodes, N4 will be the bottom here, and N5 will be the far right. So again, the green nodes there are fixed in place. So let's compute N1. That's going to look like 113 minus 000 over its norm, and that is 1 over root 11, 1 over root 11, 3 over root 11. So similarly, N2, if you wanted to compute it, wouldn't be too bad. You're just going to have a minus sign in the second coordinate, divide by the norm, and you're going to get almost the exact same vector with just, again, a minus sign in the second coordinate. And remember that these unit vectors are exactly what you use to determine the entries of the matrix A. So I'm going to just deal with the reduced matrix A, and I've numbered A1 and A2 so that I can just kill off all of the other entries. So I should have 6 columns, and the first column should correspond to putting an N1 in the first block, and an N minus N1 in the third block, which I've deleted here because I'm looking at a reduced matrix. I'm only dealing with what's going on with nodes 1 and 2. Similarly, N2, which points between 1 and 4, it'll have N2 sitting in the first block and minus N2 sitting in the fourth block, which I've deleted. So now is a pretty good time for you to try on your own to compute the entries that I'm writing in here based on the unit vectors that you should be able to compute from the picture that I've drawn. So stop as soon as I've filled in this matrix and double check that you can get all of these entries yourself. If you can't, that is a great time to come talk to me. So here's my reduced matrix A. Unfortunately, it still has a kernel, or rather, it still has a null space, even though it is a 6 by is it? Oh, okay. Well, that's not surprising then that it has a null space. So the null space is spanned in this case by 3, 0, minus 1, 3, 0, 1. And this corresponds to, well, an instability, what we were calling a mechanism. So what's going on is that if you apply a force of 3 units in the x direction and -1 unit in the z direction on the first node, and 3x and +1 in the z on the second node, the whole thing will go schmurp. And the thing is that this is unsafe for kids. This is not something you should allow people to swing on. So I want to leave it to you to decide how to reinforce that swing set in a way that, look, we could add one reinforcing bar in a clever way to get a swing set that's stable, but probably wouldn't be very swingable on. So I want to leave it to you to try to add a couple of bars to stabilize that swing set. So with that, I think we're going to end the video here.